In this video, we will see dry run of the code. Now let's quickly do the dry run of our clone graph that we just solved. Okay, and you will get everything from here. Okay, just understand the dry run completely. So let's see. This is my basically node. Okay, that I am passing here. Okay. What I am calling, I am first calling DFS node. That is the first function call that I am calling. So let's call this DFS. Okay, and I have a node. So in node I am passing 1. Basically I am calling with 1. So I will call with 1. This is my node. Okay, so I will execute this function first current node. Before that, if my node is equals to null, okay, let's understand from this. If my node is equals to null, I will return null. So node is not null, node is 1. I will create a map. So this is my hash map. This is my map. And here I am calling DFS node, here I am calling 1. And to understand it better, let's call our recursion stack, or let's simply do with the recursion tree. Okay, and we will try to understand everything. So let's create some space. Okay, let all this stuff. Okay, let's start. So we have DFS node, DFS calling with 1. Okay, I will execute this one. So this is my current node CN1. Okay, I will check if map dot has current node. So let's quickly create map, basically key value pair. So I am creating this map. Map dot has current node, no. Okay, so this condition is not true. I will come here and I will create a clone node. So I will create a clone node. So let's create a clone node. Here I will create a clone node with a value, clone node with a value of current node dot val. So with a value of 1. Okay, and I will have neighbor. So n stands for neighbor. Okay, let's see, n stands for neighbor, and inside this neighbor basically we have not put any because we have simply created with the value. Okay, so this is right now empty, but this is my clone node. We'll say clone node. Okay, once I have created, I will map dot set with current node and clone node. So I will put this node, I will mark with the red one, and I will put my clone node that is marked with blue. Okay, okay, now what I will do, okay, I will come here, I will say for let of neighbor of current node dot neighbors. What is current node neighbors? Okay, so current node neighbors, if I talk about 1 neighbors, so what are the neighbors of 1? That is 2, okay, and 4. Okay, this is in the array neighbors. Okay, so basically I will run a for loop to this array, right? And I will push clone node dot neighbors dot push DFS of neighbor. So what is this line now understand? Clone node, this is my clone node, neighbors. What I will push DFS neighbor. Basically I will push 2, right? I will push 2 here. So what I will do in my clone node, I will call DFS of neighbor. So let's again, this is a function call. Let's call this one. So from DFS1, I am calling DFS of neighbor. That means I am calling DFS of 2. Calling DFS of where I am calling me did this side, and this should be created from here because this will also go extend. But let's see. I am calling DFS here. Okay. I am simply writing D of 2. Okay. Now let's execute DFS2. So DFS2 current node. So my current node is shifted to this one 2 because I am calling DFS2, right? Okay. If map dot has current node, if map dot has 2, no it's not. So I will create a clone node with the current node dot value. So I will create a new node with 2 value. So I will create a new node with value 2, and again neighbors will be an empty array. Okay, this is my clone node. Now what I will do, I will come here and I will say map dot set current node with clone node. So current node, that is 2, I will set with the clone node, that is this 2. Okay, and what I will do, I will say for let of neighbor of current node. So what are the neighbor of current node? So neighbor of 2 basically I am asking. So neighbor of 2 are basically that is 1 and 3. Okay, so 1 and 3, basically these are my neighbors of 2. Okay, neighbors of 1 was 2, 4 and 2 and 4. So suppose if I am taking this, I am taking first the right one, then left one. So let's take in the same way. Okay, I am taking first the right one, or let's we have taken first 2 then 4. So here also I will take first 3 then 1. So I will take first 3 is the neighbor and we have 1 as the neighbor. Okay, so what I will do here, clone node.neighbor.push dfs neighbor, again one function call dfs of neighbor. That means I am calling this 3, dfs of 3. Okay, I am calling this function. So where I will call, whenever this here I am calling dfs of 3. So now first execute dfs of 3. So current node will be at 3. Again I will check, is map.has has current node? No, it's not. Again I will create a clone node. So I will create a clone node with a value of new node current node dot value. So I will current node dot 3, and again neighbor will be empty. Right. Now what I will do? Again I will run a neighbors dot current dot neighbors. What are the neighbor of 3? So neighbors of 3 are 4 and 1. So if I say neighbors of 3 are basically 4 and 1. Okay, these are the neighbors of 3. So what I will do, I will say clone node dot neighbors dot push dfs neighbor. Again one function call here, one function called dfs of neighbor, that is 4. So I will call dfs of 4. So my current node, basically I have created a clone node 3. So let me put here as 3 with this value. Now again I will call this function. Okay, dfs of 4. So I am calling this current node. So my current node will come here. Okay, is map.has has current node 4? No, I will again create a clone node. So I will again create a clone node with the value 4, current dot value cn, and neighbor will be empty. Okay, now again what I will do, once I have created, I will say map.set current node with clone node. So I will map.set 4 with the clone node 4 that I have created here. Once this is done, neighbor of current dot neighbors. What are the neighbors of 4? 1 and 3. Neighbors of 4 are 1 and 3. Right. So I will call say clone node dot neighbors push dfs of neighbor. So I will call here dfs of 1. Again dfs of 1 I will call. So when I will call this one dfs of 1, now let's see, there will be an interesting thing. When I'm calling dfs of neighbor, I will check map.has current node, that means 1. Yes, so it will return current node, that is 1. So when it will return 1, I will simply put 1 here. Okay, and can I say my dfs of 1 is done? Basically I return current node. So yes, this is done. I will move it. Okay, once this d1 is done, right, again, so can I say my this neighbor work is done, right? I have called 1 and I got the value. So this is done. One neighbor is done. Now next neighbor is 3. So I will call dfs of 3. Right. So I will call now dfs of 3. So when I'm calling dfs of 3, let's execute this one. Map.has current node 3. Yes, we have 3. So it will return current node. So it will return 3. So here I will get 3 as a value. So 1 was there. Right. Then we have 3 as a value. This is also done. Right. Blue pen. Right. This is also done. So 3 is also done. Wide 3 is also done. Now can I say is this is done? Basically my for loop is done. There were 2 things, right? And I am done with the 2 things. I have pushed the 2 things, dfs neighbor. I have pushed 1 and 3. Once this is done, I will return clone node. So I will return this 4 node, right? We were at the 4. dfs 3 is done, right? We were at dfs 4, right? So I will return this node to here. Okay. So yes, I will return this node. So can I say my this dfs 4 is also done, because it called it, created a value, and basically looped the neighbors, and this is done. So yes, this is also done. What I will do, I will simply push 4 into it, and dfs 4 is done. So what I will do, I will push 4 into it. DFS 4 is done. Okay, so DFS 4 is done. This is done. Okay, but still we are in a loop, right? We have left 1. For loop is still running, right? So I will check again. I will call this function DFS of neighbor, that is one neighbor is 1. So I will call DFS of 1 here, DFS of 1. Okay, so again when I will run DFS of 1, it will say map dot has current node, DFS of 1 is there. Yes, it is there. Return map dot get current node, so it will return 1. So when it will return, I will simply add it 1 here. DFS 1 is also done. So I will simply remove this one also from here as well, tree. Can I say this neighbor is also done? So once for loop is done, it will return clone node. So it will return this node to here, right? So value 3, DFS 3 called, right? And it will return this node. So it will return this node. So it will return 3. And my DFS 3 is also done. Okay. Now 3 is done, right? There is a next for loop call, right? Next neighbor, that is 1. So I will call DFS of 1. DFS of 1, right? So I will put DFS of 1. I will say map dot has current node. Yes, it will return. So it will return. I will simply put 1 because I will get 1 clone node. I will put 1. So once this is also done, can I say my for loop is done? Yes, for loop is done. I will return clone node. Who called it? DFS2, right? So this is done. DFS2 called this node. So this is also done, right? I will simply put this 2 node here. Okay. So this 2 is also done, right? Once this 2 is done, right? Now what is left in my for loop? That is 4. I will execute DFS of 4. So I will execute DFS of 4. DFS of 2 is done, right? DFS of 4. Now DFS of 4 will be return map dot get current node. Yes, 4, we have 4 node. So I will add 4 node here. Okay. I will add this. So can I say 4 is also done? Once this is done, I will return the clone node. So I will return this node to DFS1 that I have called. So I will return this node to here. So this is also done, right? And this will be my complete clone node. Here in this node, here we have a node 2 and node 4, and those have also clone node. So this is how this function is working. Okay, I hope you are getting this. This was dry run. Okay, I hope you are clear with it. Okay, so basically this is how it will work. Okay, and this will be the simple DFS of our clone graph. Now let's quickly talk about the time and space complexity. Okay, so what will be the time complexity of it? So here we have 4 nodes, and you can see we have called 4 function calls, right? But basically here in graph, the time complexity is basically big O of V plus big O of E, or I can say simply big O of V plus E, where V is the number of vertices. Okay, vertices is basically your nodes. Okay, and E for edges. Okay, so these are basically edges. Okay, so here the time complexity here will be same as big O of N plus big O of N plus E, that is edges. Why? Because we are visiting each node only once. You can see we are using map data structure, right? So I have visited once. Okay, 1 was not there, so I created it and I put it in the map. So I am not visiting 1 again, right? So that's why it totally depends on the number of nodes, okay, and not any proportional of it. Whatever the number of nodes, my function calls will be that limited to it. Okay, why now it's depends on the edges? Because each node has neighbors, right? Like for 1, 2 and 4 is neighbor. So I am visiting 2. If it is not, I am creating it and then I am visiting their neighbors. So I am visiting 2 and 4, their edges. So on each edges also I am visiting it. So the time complexity will be big O of n plus e, big O number depending on the number of nodes and the number of edges. Now let's talk about the space complexity. So for space complexity, it will be number of nodes only, because basically you can check your recursion is stacked till when the nodes are not there. So one, basically you called one has a number of 2, so you called 2 has a number of 3, so you called 3 has a number of 4. So the auxiliary stack, the recursion stack can reach to the functional calls, right? So basically number of nodes. So if there is node 1, I will call, then 1 call with 2, then 3, then 4. Okay, so this is of auxiliary space. Okay, basically auxiliary recursion stack space, and this map that I have created, right, that is also big O of n. So basically both, if I take, right, so the average time complexity will be big O of n only, right, because 2n, that is still an order of n, so it will be big O of n. N for this one, the space that we have created, and n for the auxiliary space that we have created in the recursion. Okay, so this will be the time complexity and space complexity of this problem by using DFS. Okay, now let me quickly give you a hint about the BFS. Basically, if you know about BFS, exactly same, I will simply paste the code here and we can check how BFS is working. So now let's quickly check the BFS code. Exactly, BFS in we use basically queue data structure. There won't be any recursion calls. So let's see BFS calls. So I have created a map. Let me quickly add a map here as well. So we have this map. This is my map. Okay, with key value pairs. This key and value. Okay, so I have a map. Okay, I have a queue, and in the queue I have added the node. So I have added 1 here. Okay, this. Okay, once I have added, I have said map.set node with the clone. So I will first create a clone. I am creating a clone. So again, let's take blue pen to create a clone. I have created a clone, right? And I have added here. Okay, so I have added 1 here, 1 and its clone. Now this is done, right? In the queue, you have the actual node. Now while queue.length is not equals to 0, so here it is not equals to 0, my current will be queue.shift. So this will be, basically I will simply take out this one. That is the meaning, right? So I will simply take out this one, and I have now here 1 with pointing as current, right? Now current clone will be map.get current. So I will take the current clone 1. So I will take 1 as the current clone. Okay, now basically again same, exactly same neighbor of current dot neighbors. So its neighbor, so what are its neighbor? Its neighbor is basically 2 and 4. Okay, so let me say it's like this, that we have a neighbor here 2 and 4. Okay, or let's say 4 and 2. Okay, so 4 and 2, so it will check is map dot has neighbor. Basically it is not. If map dot has not neighbor, so if 4 is not there, yes, 4 is not there, neighbor is not there, 4 is not in the map. So what I will do, I will say map dot set with the neighbor and the clone neighbor. So basically I will set 4 with its clone. Okay, this is done, and I will push the neighbor. So I will basically push the neighbor, that is I will push 4 here in the queue. Okay, now once I have done it, basically remember how this is work. It works on the level wise. We basically put the node in the queues. Okay, that is the BFS travel. So we put the node in the queue, we take out its neighbors, and then we will check out for the neighbor's neighbor, and then we put neighbor's neighbor in the queue. Basically this process goes till queue.length is not equals to 0. Okay, so I have pushed neighbor 4. Okay, once this is done, what I will do, I will check for the next neighbor, right? So what is the next neighbor? See here, this is the if condition. I have pushed it, and after this I will push in the I will push in the clone neighbor. So I will push here as well. I will push the clone neighbor, that is map.get neighbor. So I will get 4 and I will push it here. Now after this if condition, again I will check for the next neighbor, right? So this 4 is done. I will check for 2 now. Okay, so I will check for 2. Is 2 is present in the map? No, it's not. So again I will create 2, right? And I will add a clone of 2 here. Once I have added, I will push 2 here as well, right? Once I have done with this one, I will simply push 2 in the current clone here. Once this is done, right, for loop is done, right, I will again check in the, because I am in the while loop, I will say q dot length is greater than 0. Yes, it is still greater than 0, and both the neighbors are done, right? 4 is done, 2 is done. Okay, so basically I will remove from here. Okay, now what I will do, again current will be q dot shift, so I will remove this 4. So my current will point to 4, right? So if it is pointing to 4, my current clone map dot get current. So do we have a clone of 4? Okay, do we have map dot get? Yes, we have. So what I will do, my current clone will be 4 now. So here as well, I will take 4. 4 loop. So current clone will be map dot get current. So I have that 4. Okay. Now again neighbor of current dot neighbors, 4 neighbor, that is 1. Okay. So if I'm taking 1 was 4 and 2, so 4, 3 and 1. I will see 3 is the neighbor and 4. 3 is the neighbor and 1 is the neighbor. So I will check here. Again now neighbor to neighbor. So I will check these two neighbors one by one. So I will first check for 3. So if map dot has neighbor 3, yes. So 3 is not there. Yes, it is not there. So what I will do, I will put 3. I will put 3 and I will put the clone of it 3, right? This I will done. Once I have this done, I will push in the current clone also 3. So I will push 3 also here. Once this is done, right, I will check the next neighbor. And see, I have pushed the neighbor, so I will push 3 as well here. So I will push 3, right? Once this is done, right, 3 is done. So I will come here, I will come to 1. Now is map dot has neighbor 1? So yes it is. So I won't come under the if condition. I will simply say current dot clone neighbors push, because 1 is already there. So why we don't need to, why need to push here in the queue? Okay, and why need to create a clone? If 1 is already there, what I will do, I will simply put 1 here. Right, now my for loop is done. Yes, my for loop is done. Again, is q dot length is greater than 0? Yes, q dot length is greater than 0. So what I will do, I will say current is equal to q dot shift. So this 2 will be come here. So now this 2 will come here. Now I have added 2. What I will do, again my current clone will also be 2 from here. So my current clone will also be 2. Right, now what I will check, if map dot has neighbor. Yes, not neighbor. So no, 2 has a neighbor. Yes, we have present 2. So what I will do, I will simply add 2's neighbor. Okay, first of all, let's see current clone. Yeah, neighbor of current dot neighbors. So first of all, run with this one. So we have 2, 1 and 3. Okay, so what I will do, once this I have done it, I will check neighbor of current dot neighbor. So current dot neighbor is 1. I will check is this is present. Is map dot has neighbor 1 neighbor? Yes, we have. So I will simply add it. This line I will execute. Now if condition won't execute. 3 is present. Yes, present. I will simply add it 3. This is also done. Right. What I will do, I will shift. Basically, I will say again, while q dot length is greater than 0. Yes, it is. Again, I will shift it. So I will shift it. Get 3 here. Okay. And I will get the current from here. So I will get 3 from here. Again, I will check the neighbors of 3, that is 2 and 4. So I will check for 2 and 4. Right, now for 2 I will check neighbor of current dot neighbors, that means 2 and 4. So I will check if map dot has neighbor. So 2 is there, I will simply add a 2. 4 is there, so I will simply add 4 here. Right, no need to push q because that is present in the map. Okay, if it is not present, then I need to create it. So no need to do. Right, this is also done. So once this is done, right, once this is done, I will check is my q dot length is greater than 0. No, it's not. So here while loop will end and I will return the clone, right? So basically what was my clone, right? Clone was new node dot value, that is 1. So I will return the 1 clone. So basically I will return 1, right? And now 1 will have all the members, okay, basically neighbors. So this is how BFS works. And again, the time complexity will be same, that you are visiting each node exactly once. So again, the time complexity here, even in this case, will be O of V plus E, right? So because you are visiting each nodes, right? You are basically in the queue. We have all the nodes, all our 4 nodes. We are visiting each node one by one, and it depends on the edges, right? If we have the neighbors, we are adding in the queue, right? And then we are executing till my queue dot length is greater than 0. So basically, this is how I am working. Okay, and you can see, right, this is not running simultaneously, right? So you can understand maybe n square, no, okay, because when q dot length is greater than 0, this for loop is running separately, okay. So again, it depends on the number of vertices and the edges, okay. The space complexity will also be same, right? Here will be 2 data structure will be used. One is q, again it will carry the number of nodes, that is again depends on the total number of nodes. And here also we have total number of nodes. Again the time complexity will be in order of n only, okay, big of v. So it will be big of v only, that is number of nodes, because either you are taking map or queue, right? It is depending on the number of nodes only, right? Here you are storing nodes, here you are storing nodes. It will be depends on the number of nodes. Again exactly same as our DFS. Number of nodes will come here, the space complexity, and here number of nodes plus edges, nodes plus edges, right, in the time complexity. So exactly same time complexity as our DFS, right? We go of n plus e, number of nodes I am returning, and native we go. Okay, so this was all about clone graph. I hope you got it complete, DFS approaches and BFS approaches. Okay, now we will see more problems on graphs. Okay, so go ahead with the series, there are more problems graph.